this theta function, theta LU, was considered in the book of Eichler-Zagier, and now I would like to analyze this function as generating function. The generating function for what problem? First of all, let's consider our first function, theta, in one variable. Then, all Fourier coefficients of this function are equal to R, L, to N, Q to the power N, where N is greater or equal to 0, and where R is the number of representation of 2n by the quadratic lattice L. What Fourier expansion we get for the Eichler-Zagier theta function? If we analyze the definition of this function, we have to fix the square of vector v and the scalar product of v and u. It will be an integer. So, and we can collect the e function with the same 2n and L. We get the following Fourier expansion for the theta function. The sum is taken over all n and L in Z, R, L, U, N, L, Q to the power N, R to the power L. Q in both cases, this is e to the power 2pi tau, and R will be e to the power 2 pi I z. So this is the second exponent, the exponent of the second variable z of our theta function. The partition function, or the Fourier coefficient R, this is the arithmetic function of the following type. This is the number of all vectors in L such that square is equal to 2n and the scalar product with u is equal to L. So we analyze a distribution of the vector with fixed norm and a fixed scalar product with the vector u fixed. So what function do we get here? Why this function, for example, is interesting? For this, we have to analyze one very, very classical and very, very important lattice. But for this, I would like to maybe we analyze this lattice in some detail later, but now I would like only to fix it. So notation for it, E8. This is an even integral lattice of determinant 1. Let's assume that E8 is equal to L. So we consider this case. We consider the corresponding Jacobi theta series for L equal to E8. And now let's assume that U is the root of this lattice. A root means a vector of square 2. Then, maybe you know, maybe not, but we discuss, as I told you, we analyze all these lattices in some details later. The orthogonal complement to U in E8, this is a so-called lattice E7. So, let us analyze the function R for the lattice E8 and for the root U for n equal to 0, for L equal to 0. This is the number of all vectors in E8 with fixed norm to n and with the scalar product 0 with U. So this is all vectors of the norm 2n orthogonal to U. But all orthogonal vectors belongs to E7. Therefore, we get the number of representation of 2n by the lattice E7. So studying the Jacobi theta series of this type, we can analyze this function, the number of representation by E7, which is much more complicated than the number of representation by E8. In our course, for example, we get an explicit formula for this arithmetic function. The generated competition function are two motivations for the theory of Jacobi forms, but now I would like to give you one more motivation. I would like to analyze elliptization of the Ramanujan delta function. But to consider this elliptization, I need the definition of modular form, classical modular form in one variable. So now we consider the modular form with respect to the modular group SL2Z. Definition. A modular form of weight k is an integer, with respect to the modular group SL2Z, is a holomorphic function f on the upper half plane, which satisfies the following modular equation for any A, B, C, D matrix in SL2Z, and which has the following functional equation: f tau is equal to the sum a n e to the power 2 pi I n tau. The summation is taken for all non-negative n. This is the very classical definition. And first of all, why we need this additional conditional Fourier expansion? First of all, according to the first equation for the translation lattice, T, f is periodic, and we consider Fourier expansion. And this Fourier expansion tells us that the function f at tau is holomorphic at e infinity, or in other words, then the function phi at q, where q is equal to e to the power 2 pi tau, is holomorphic at q equal to 0.